One more Julia talk today. So I am working at Purdue right now. And let me see if my slides work. Okay, they do. So I'm a postdoc at Purdue right now, and I've been doing Julia during my PhD for a bunch of years at Northeastern. These days I'm doing many crazy things with compilers of sorts, various sorts. It may look like it's all over the place. In fact, there is like a foundational theme is like how to compile tree-like structures efficiently and how to accelerate tree traversals. So these all projects are more or less about this stuff. And I managed to put 3 LambdaConf speakers on this picture, and my wife and my kid. So that was fun. Other than that, as I said, I'm gonna be talking about performance and how Julia tries to achieve it. So first, very high level, I'll give you the worst kind of lies, which is micro benchmarks. On Julia's own website, they say that they are pretty close, not far off from C, which is on the left here. It's like the baseline, and there is like a bunch of programs, small programs, and what you need to sort of the high-level takeaway of this set of benchmarks, there are more or less roughly two clusters of languages: those that run fast, like Rust and Go, and those that run slow, like Python, R, and other mathematical or the scientific computing languages. So Julia somehow squeezed into the former category, although trying to look alike with the guys on the right. So how does it work for it? Let's see. So one of the core features that I will be talking about, the Julia, if you want to take away one thing from these 2 talks, probably, is that Julia is designed around multiple dynamic dispatch, and it's type-driven, meaning that Julia, when you have the simplest kind of code, like summing up 2 integers, it will go over the method table. It will find all the pluses, which in the standard library, they have 206 methods for plus alone. And it will try to pick the best one in some sense. And that you can imagine that in general, it may be a slow procedure. Somehow, Julia makes it fast. I want to highlight the type-driven part here. So types in Julia play 2 roles actually. So one is they help to structure programs around this, various methods. So you'll see every method here. So every signature here stands for like a whole method. It may be many lines of codes, some sophisticated algorithms sometimes. So all of them only differ. So all of them should be different, at least in the signature. So in the kind of types you have in the kind of types you have in the parameter list. So that's what I mean when I say structuring programs around types. But other than that, the second goal of types in Julia is to guide the optimizer, and that's what I'll be talking today, rather than how to do how to write programs with all that many pluses, for example. So types are everywhere, so you need to make sense of them. You need to try to split them in several categories. So first ones, the concrete types, for everyone's beloved bools and ints and floats. They're actually called primitives and are not exact. So these are built-ins, but you can define your own primitive types in Julia, which is not very common feature in many programming languages these days. So primitive just means the bit representation of a type. So how many bits? They're semantics, more or less. Usually you don't define all that much new primitive types in Julia programs because these maps nicely on LLVM, which Julia uses as a backend to do the actual binary code generation. What people do much more often is that they define structs, which are aggregates of several other types in Julia. So in this case, for example, add is a new struct that is a subtype of the expr type, and it has two fields, left-hand side, right-hand side of the addition, presumably, which both have types expr. So expr in this example is an example of a user-defined type, which is an abstract type. So that's the other group of the types. And any is the most flexible and least informative one. But still, if you want to appeal to the audience who are used to dynamic languages, you have to have some sort of wildcards in your code. Sometimes you want just to not bother about the types at all. So that's what any allows you to do. Sometimes you have something more interesting. If you have a couple already known types, you can build a union out of them. So unions are also abstract types, and yeah, expr, as I said, is a user-defined type, and Julia just told you that abstract types don't have fields ever, so they participate in multiple dispatch and stuff like that, but there is no like actual data fields inside. So a little bit more like a rundown of concrete versus abstract. Optimizer is happy when it sees concrete types because it knows what memory layout is there, so what are the fields, what their types are, and stuff like that. Whereas abstract types is just a pointer. It's usually just a pointer somewhere. Optimizer cannot assume anything about these kind of types. Usually you create values applying constructors of concrete types or using literals like 1, 2, and hello world. And then there is also type inference somewhere because, as you already heard, Julia is a JIT compiled language, so there is some interesting stuff going on during compilation. So type inference is part of it. And type inference will sometimes figure that the types of intermediate values are concrete. Sometimes it will not be able to do so it will think that some things are just abstract, so opaque. And yeah, so the mission of concrete types is to facilitate optimizations, but really they just the little tags on the values that you create. And abstract types are nice for defining all those overloading, all those many methods for one operation. And examples I already showed you. Let's see. So my claim is that types have to do with optimization, right? So let's see a little example that is supposed to convince you in that. So there is a small function that just sums the vector, the input vector v. You see there is no type annotation in this case. In general, there may be. So it means any. So we don't know anything about it. So the code hopefully is self-explanatory. And we perform two experiments. First is we pass a vector of floats as the input, and we say that the triple question mark is just 0. So we literally put 0 in there. So we initialize the sum with the integer 0, and it runs for 24 microseconds in my laptop, I think. And so the second experiment is exactly the same input, but the initial value is a floating point value now, and the runtime is more than twice as fast. So clearly, if you don't care all that much, as Julia was answering one of the questions before, if you don't care all that much about performance, you can put whatever you want, but if you do, you need to scratch your head a little bit and figure out that it's the right way to go is the floating point value. So when people stuck with problems like that, so sudden performance losses in some computations like that, hot loops, computing, going over a lot of numbers, what they do in Julia, well, they fire up the REPL and they will say add code-word type and the call to the target method with the target inputs. And code-word type is a nice utility that allows you to inspect the internal representation of the method as compiled for this particular input type, in this case, vector float 64. And the name of the function should be sum, of course. So the internal representation is ugly. Do not recommend reading it, although Julia hackers, usually, not the users usually, but the library authors do have to read it a lot. So just a long line of more primitive kind of assignments that Julia compiler splits into your code. So there are some, mostly just the call to the methods, assignments of constants is what you see on the right-hand side. On the left-hand side, those are virtual registers. So if you ever heard of SSA, static single assignment form, in compilers, that's more or less what it is. And so Julia will, so that here, I used red, fat red, and then blue for concrete and red for abstract. That's not me doing it here. It's Julia printing it out like that. So it tells you something. In particular, it wasn't able to figure out the concrete type for S, for the sum variable. So it will say, well, it's a union of float and int. So you can imagine that it may be an empty vector. You will never get inside the loop, right? So if you get back to that example, if you have an empty loop, so it really depends on what you initialize it with. So which value will be returned. So it is not sure what kind of value S is. So that's the problem. And this property, it has a general name called type stability. So if you have a method that Julia always able to infer a concrete type, then we call this method type stable. So obviously the sum with the integer initial value, right? When you initialize it as integer 0, it's not type stable because Julia wasn't able to figure out the type, the return type, a concrete return type. And so why, in a nutshell, why it has to do with optimizations is that we know that type stable code is good because it allows to devirtualize or remove as much dynamic dispatch as possible ahead of time. So imagine, remember again those 206 overloadings of plus. It's a very slow process to figure out which plus is needed. So you would rather have it figured out ahead of time. So that's what I call devirtualization. Type stable method allows devirtualization. Type unstable ones, not so much. And devirtualization allows a lot of classical optimizations. Your unboxing, inlining, is everything that you find in more usual languages. So that's I showed you an example of this phenomenon, the type unstable code in this case. So what I want to show you now is whether how exactly JIT uses this property type stability to remove multiple dispatch to devirtualize. That's a little bit more technical, but bear with me. Let's see. So I want to give you first a 1,000-feet overview of how Julia JIT works, which is, so you have a program. Program may be a list of statements in your script. So Julia uses scripts, or so source code. You just run your source files. You don't have compiled artifacts usually. So in this case, our program is just a call to some function f with 2 arguments. And so important part of the state of your program is the method table. So method table stores all the known method definitions at this point in time. So there is one f, let's say it's the only one in the method table, and it doesn't have, so there is some definition to it, and there are just any's as the type annotations of the arguments. So this f will be called or will be dispatched to execute this program. If we didn't have a JIT, that is. So if we do have a JIT, and you can call Julia with -0 and it will turn off the JIT part. But of course, no one really does that most of the time. So what JIT does is it thinks real hard, scratches its head, and adds another entry to the method table. So now you have a little bit longer of a method table, and it adds another f in it, and now it's f with the annotations you see int and float. So that's 1,000 feet overview again. What JIT does, it tries to extend your method table with more efficient, supposedly more efficient implementations of your methods. And now, of course, we dispatch to this new, so to execute this program, we dispatch to this new definition rather than the original one. So now we have a little intermezzo which I will jump to what JIT actually does to compile F to that optimized version. But first, I will be using this notation that we call joules. And that's more or less that SSA form that I mentioned before, so just a bunch of assignments with the primitive right-hand side. So that's a simplified version of that internal representation, which has type and precision. It can reason about type and precisions in that there are two kinds of types, abstract and concrete. And also the second important feature is that it can reason about dispatched calls versus direct calls. So dispatched calls are normal Julia calls which go through this horrible procedure of trying to figure out which of those 206 pluses you need to take to execute the program. Whereas dispatch calls are direct calls are super efficient. It jumps right into the function that you are supposed to implement. And so now the most technical slide is this one. So bear with me. So we try to compile F for a couple of inputs, concrete input types, int and float. So we take the method body of F from the method table. We first run type inference. Type inference, it's more or less a straightforward sort of data flow analysis. You know the inputs. You sort of try to propagate them as much as you can and type every slot, every virtual register, right? So in some cases, for some registers, type inference will succeed. It will say, for example, it knows that register 3 will be of type int64. But, for example, it may fail to type infer the second register, type of the second register. And as a result, so based on this information from type inference, we come up with the extended method table, which now has the new F compiled for int and float. And you'll notice two differences. So first is that we replace the dispatched call with the direct call. So direct call has this exclamation mark and the types of the inputs. And in this case, it will need to generate another version of G with these particular types of arguments. It doesn't have to be the case. It may be a pre-existing function sometimes. So that's a direct call. So that's a success. We devirtualized. So we removed one of the expensive multiple dispatches here. But not everything is rosy here, because the last call to H is not devirtualized because we don't know. So it just happens that type inference wasn't able to figure out the type of %2. So it will not know. It will not know what H to call because it doesn't know the type of the input argument. So we also did a little evaluation study of what happens in practice. Do programmers write type stable code, mostly type unstable code? So we took 1,000 Julia packages, top packages sorted by GitHub stars. We ran their tests because you will notice that in order to figure out whether a method is type stable or not, you need some inputs. So test is a natural source of figuring out those inputs. So we can compute the type stability, we can compute various different metrics. So sometimes control flow is so type unstable methods will be those sometimes with more sophisticated control flow, with more ifs and fors and stuff like that. And so sort of a side note is here is that tests, of course, are not a complete picture. It can't give you a complete answer. So we have another work that tries to approximate type stability without like running anything, or without like even having a test suite, but ask me later if you're interested. So mostly Julia packages are type stable, so it means like 2/3 or something like that are type stable, and so that's good enough. And we zoomed for the top 10 packages, but I will skip this for the sake of time. There's also qualitative analysis when we try to look at the particular packages and see how type stable and unstable code looks like. Also, skip this for now. So my bottom line is that Julia has an interesting JIT. It's both simpler than other competitors for other languages, and it's also oftentimes more powerful than those. Have no starting typing whatsoever, but has types, and those types are precious, bear some precious information to the compiler. And as a sort of bottom line, I'm not selling you Julia. I'm not working with the Julia team. I was curious about the language. But I hope you're curious about it too now. And I hope you were able to appreciate compilers that are driven by types. That's it. Thank you.
Thank you so much. That was super cool. Bear with me while I ask this question, because
Sure.
this is all new terminology to me. I was curious, though, on slide 15, where you showed the kind of compiled version of an ideal method to call, that syntax of G, bang, and then the type definition, is that something that you can use in line to specifically reference a method in the method table?
It's a great question, because it's exactly what is not available to Julia programmer at all. So that's what we came up in our little formalism that we call joules, in order to be able to reason about what is the good code and what is the bad code. So good code is where you have bang, bang, bang. So it's opposite of Haskell, right? In Haskell you have bang, bang, bang. That means someone was trying to figure out strictness. Okay, doesn't matter. So in this case, it's our sort of notation that we mark the code when it's good. In Julia, even when you get to the level of code-worn type that I showed at some point, you will not see this kind of bangs here, unfortunately. So they will not know whether it was a success virtualization or not. Does this answer the question? Okay, cool. Okay. Any more questions? Well, I will show you the website. Yes. No? Yep, Julia.
So in the running example, you showed that having floating 0 with a vector of floats is good, but then what happens when we call our sum with a vector of integer and the floating 0?
Yeah. So I believe it's kind of the same problem if it's the other way around. So if you have a vector of integers as the input, and you have so this, if you just put 0 point, so whatever you put, so I guess your point is that if whatever you put here, you can come up with an input that will or not run fast. That is correct, and Julia has means to be more flexible about it. So instead of writing 0 or 0.0, you will rely on multiple dispatch. So you'll call the method called 0 of v, I think, or v square brackets 0 or something like that, or L type of v, something like that. And then, so the multiple dispatch will should be able to figure out what 0 to put there, and then the JIT compiler will be able to eliminate multiple dispatch while it compiles for vector of ints or vector of floats. So there are ways, there's reasonably well-known ways to avoid pathologies like this one, when you don't know which value best used. But certainly there are trickier cases where there is no one good solution. It's hard to sort of figure out how to make your code running fast. Yeah.
Cool, thanks.
Thank you.